So, when we want to analyze a system that has forces acting on it, there's a very systematic way that you can go about doing this. Suppose we're going to take an example. So, suppose I have a box, and this box has a mass of m, and it's sitting on a table. Okay? And let's say that I'm pulling this box with a force that I'm going to call F. Alright? So this is a really straightforward example that we're going to do first. Then we'll move on to a better, more complicated one. So the first thing you always want to do in a force problem is figure out what object is relevant. What are we asking here? So this problem I'm going to ask, I'm going to say find the acceleration of the box. Which means the relevant object is the box. So step one, we're going to say a relevant object is the box. For step two, we want to draw free body diagrams of our relevant objects. So a free body diagram is a way of visually demonstrating what forces are acting on an object. So when you draw a free body diagram, there are certain things that you do and you don't do. So you always, it's called free body because the object is separated from everything else. So you pick the relevant object, the box, and that is the only thing you're going to put in your free body diagram as an object. So you have a box. Okay? Generally it's good to just draw a box or a circle as your free body diagram. Some people use just points, dots. And what you're going to do is you're going to draw all forces acting on this object. Every one. So it feels a force to the right of F. Good. It also feels gravity, right? Anything on Earth is going to feel gravity. So it's going to feel the force of gravity down. Now, remember, we mentioned that Newton's second law says that F is equal to mass times acceleration, right? We know the mass of the object. And it turns out there's a certain acceleration due to gravity. And if you've seen the kinematics videos, we talked about that. And that is called g. And g is 9.8 meters per second squared. So the force of gravity down is mg. But if you ever have an unbalanced force, it's going to move, it's going to accelerate in that way, right? So if we have mg down, we know the box isn't going to fall through the table. There must be a force up. And indeed there is, right? You have the normal force. Normal force is the force of the box, the table pushing on the box. And that's going to be equal and opposite. I want to clarify that this is not a third law pair. The third law, Newton's third law, says for every action you have an equal and opposite reaction, right, for forces. So the first force being felt is the table feels the weight of the box pushing on it. So if we drew a separate free body diagram for the table, we'd have a force down of mg. The reaction force is this mg. You're never going to have third law pairs acting on the same object. That's the first test. If someone asks you to label or identify third law pairs, if it's on the same object, they're not third law pairs. And those are the only forces we have acting on this. So that's going to be our free body diagram. Step 3 is to choose our coordinates. So generally, when I say choose coordinates, you mean you want to choose right or left and up and down to be positive or negative. In this case, it's not moving up or down, so we don't have to worry about that, but it is moving to the right. So we're going to say that right is positive and left is negative. So step 4 says we want to write down our force equations. What this means is we want to calculate the net force. So there's two ways of writing this. You can either write F net, or the way that I prefer is to write this symbol, which is sigma, and it's read as the sum of all forces in the x direction. That's what that means, because we're moving in the x direction, not the y direction. And all you're going to do is you're going to add up all of the forces that are in the positive direction and subtract any forces in the negative direction. So, positive forces, and you're subtracting the negative direction forces. So if we go ahead and do that for this problem, we're going to have that the sum of forces in the x direction is equal to our positive forces F, and we have no negative forces, so we don't have to subtract anything. What do we set this equal to? Well, we set this equal to the net force. And the net force is equal to ma. Right? Newton's second law. The net force on an object is mass times acceleration. If you add up all the forces on the object, you're going to see what is the object's net force acting on the object. So this is equal to ma. So in this case, A equals F over M. That was step 5, solve. So in this case, you really could just plug it right into F equals ma. But I wanted to walk you through how to use this system for a really simple problem. Let's do a more complicated problem. So this time, let's say I have a box, again, but this time the box of mass m is being pulled up by a force F, and it's hanging in the air. Okay? So, step 1, identify relevant object. It's going to be the box. Step 2, draw our free body diagram. So we draw our box, and we have a force up on it, right, of F. The force down is going to be gravity. It's field's gravity, right? So we're going to say mg down. Step 3 is choose your coordinates. So I'm going to say up is going to be positive, and I'm going to say down is negative. And that brings us to step 4, where we actually write our force equations. Step 4, let's write our equations. So this time we're operating in the y direction, right? There's no forces acting in the x direction. So we're going to add up all the forces in the y direction. And that's going to equal our positive F minus mg, because mg is down. And that's going to be equal to the net force, which is mass times acceleration, ma. So from here, we can solve this for a, right? It's asking us for acceleration. So we have F minus mg equals ma. Divide both sides by m, and we get that a is equal to F minus mg divided by m. And that's our acceleration. And this is how you can approach essentially every single problem that has only one object in it. Once you have multiple objects connected, it gets a little bit trickier. But for one object, all you're going to do is identify what object you're interested in, draw the free body diagram, choose your coordinate system, set up your force equations, and then solve the one force equation that you have for acceleration. Usually it's going to ask for acceleration. I could ask, we could do another example where I say, suppose, so I have a force acting up of F, and let's say I'm also going to tell you the box is accelerating upwards at a rate of A. So we want to say, what is F? In order to give a box an acceleration of A, what force do you need to apply? You need the exact same thing. Relevant object is box, still the same free body diagram, same exact coordinates. Our force equation is also the same. It's equal to F minus mg equals ma. But this time you want to find F, right? What force will give an acceleration of A up? So you're just going to say, okay, well, we'll add mg to both sides, and we get F is equal to mg plus ma. You can simplify that and say F is equal to m times g plus a. So if you want to give a box hanging in the air an acceleration of A upward, you have to apply a force of m times g plus a. So it won't always ask you to solve for acceleration, but generally acceleration or find some kind of force or something like that. And that is the system that you can use to solve every force problem with one object.